and welcome to the third SOLAR workshop. The way it works is we're first going to present basic genetic data. That first presentation will be given by Dr. Vincent Diego from Southwest Biomedical Institute, and he's presenting instead of John Blangero, who got really sick and couldn't attend. But the idea of the first workshop is to introduce people who are knowledgeable in imaging but not knowledgeable in genetics to the basic genetic concepts. The basic genetic concepts are actually quite simple, and since most imagers are very quantitative in nature, I think it really doesn't take a whole lot of time and effort to understand what is going on, because it's actually a very simple idea and the concept of analysis are very simple, and I'm sure Dr. Diego will do a brilliant job explaining it to us. So he'll go into the basic genetic analysis, he'll talk about how relationship and genotypes can be used for providing important contrasts. After his presentation, I will be back at the podium and I'll be talking about SOLAR-Eclipse, which is a statistical genetic analysis package that has over 2 decades in development, and we are currently working to make it more readily available for analysis of imaging phenotypes. After that, we will have 2 sort of real-world application examples. What can you do in SOLAR? And we should be very pleased because one of the presenters is Nada Jahanshad, and she has done really pioneering job on using SOLAR to sort of in the concept of a large consortium studies where you can extract huge improvement in statistical power by combining in multiple pedigrees. Then Dr. Bennett Landman from Vanderbilt will present an analysis on how SOLAR and OpenMX produce similar measurements when used on the same phenotype. And finally, Thomas Nichols will present some additional thoughts and summarize what has been done in the last year and what shall we expect in the next year. Well, without any further ado, Dr. Diego.
So if I'm going to stay here, I should not turn the mic on? Is that right? Let me see. All right. So we had a name change for various reasons. We're no longer the Southwest Foundation. We're the Texas Biomedical Research Institute. And the main goal of my talk is just to really show how statistical genetics can be made simple. And I want to highlight the basic statistical genetic model and show how you can rationally and strategically make the model a little more realistic. All right, so I want to start with a little historical background and show how statistical genetics can be bridged with Mendelian genetics and how this historically developed. And I want to briefly mention this conceptual bridge connecting Mendelian genetics to the statistical genetics of complex traits. Of course, modern genetics starts with Gregor Mendel. He's known as the father of modern genetics. Is there a way to face the screen? There you go. All right, can you hear me? No. No?
She's going to turn up.
Okay. Are we good? All right. So Mendel was known as the father of modern genetics, and in about the mid-1800s, he performed numerous experiments on crosses with pea plants. And He proposed what would come to be known as the Mendel's laws of inheritance, the law of segregation and independent assortment. Particles of inheritance, in his terminology, or the terminology of that day, segregated generationally from parents to offspring, and that they did so independently of one another. And his system was mainly all of the traits relevant to pea plants, right? And so his work, in the middle of the 1800s would lay fallow for several decades until the rediscovery and promotion of his findings by these gentlemen here, Hugo de Vries, Carl Correns, William Bateson, and others in the early 1900s. Now, a little earlier, before that, there was a rise of British biometry, following after the tradition of Francis Galton. And the chief proponents in the early 1900s were Carl Pearson and Walter Weldon. And in the early 1900s, there was this vigorous debate between what were known at that time as the neo-Mendelians, because his work was just recently discovered, or rediscovered, actually. And so there was this debate between the neo-Mendelians on the one hand and the biometricians on the other regarding the genetic determination of complex traits. And the neo-Mendelians, of course, posited that somehow the laws of Mendel's laws have to be obeyed, and they have to be involved in the determination of complex traits. And the biometricians were at the time unable to see how that was possible, so they kind of rejected that notion. And so there was this debate for about maybe the first decade, or the better part of the first 2 decades, and it was finally resolved in this seminal paper by Ronald A. Fisher, published in this obscure Transactions of the Royal Society of Edinburgh. There's a backstory behind that, but I don't have time to get into that. All right, and so I'm going to call this, in that paper he published this brilliant idea, and I'm calling it the Fisherian bridge between Mendelian genetics and statistical genetics. And so in this paper he reconciled the Mendelian segregation of genes with the determination process of complex traits. His model assumed that complex traits were determined by a large number of genes, each one exhibiting Mendelian segregation with small additive effects. This is the polygenic model, right? The term variance is first coined here in the modern-day linear model, along with the use of the normal distribution traced back to this paper. And this is just a schematic diagram kind of illustrating the logic behind Fisher's argument. And recall that his argument assumes numerous loci that are involved in the genetic determination of a complex trait. And this is just an example of simple system skin pigmentation involving, just for this example, 3 loci, right? And in the horizontal categories, this is probably better, represent all the potential genotypic, all the potential combinations for the gene types. And the histogram plot just gives a frequency diagram of all the their expected frequencies. And you can see that already for a system determined by just 3 loci, it's already hinting at an approximation to the normal distribution. And it can be shown, and has been shown in numerous genetics textbooks, that as the number of loci increases, usually from 10 and up, the approximation to the normal distribution becomes very good. For numerous loci under Fisher's polygenic model, the approximation becomes more and more perfect, right? And let me see here. So the idea here is that we can treat this, the aggregate effects of this system of genes as a normal distribution, right? So therefore, if a complex trait is underlain or determined by many genes, each one with additive effects, we may confidently assert that the trait exhibits a normal distribution. This is somewhat justified by the central limit theorem We don't have time to get into that. But this concept is the bridge between Mendelian genetics and modern quantitative or statistical genetics. Now, it also means that we can model complex traits using the two main properties of the normal distribution, the mean and the variance. All right? All contemporary variance components models are really just more sophisticated elaborations of this very basic idea, right? That we can model a trait, a complex trait using the normal distribution. All right, and so I want to be explicit about the assumptions of the linear model, right? And then I'll go over some departures and briefly mention how those departures can be addressed, and then I'll go over a basic construction from the univariate version to the multivariate version of the linear model. And so the main assumptions are, think back to statistics and your first course in statistics, and to that part of the course where you're talking about linear regression. These are the exact same assumptions, right? Additive effects the effects are additive, or they exhibit a simple linear structure, and we'll see a little figure about that. Traits are multivariate, normal in distribution. The observations are independent. There's no correlation structure describing them, and the variance is homogeneous across observations. All right. And so this is just a diagram of what's meant by additivity, and we can think of this simple single locus, diallelic locus, for some trait on a scale of arbitrary units from 1 to 3, I don't know, hobbit height or something. And you can think of the categories as the dose of the big A allele. And so this first category has 0 big A alleles, the second has 1, and the third has 2 of the big A alleles. You see, with the addition, starting from 0 of the big A allele all the way up to 1 and then 2, you get this additive increase in hobbit height, right? No big A allele, you have 1 foot. 2, you have 2 feet. And 3 of, or 2 big A alleles, you have a height of 3 feet. So that's what's meant by the term additivity. And this slide is meant to illustrate the three assumptions that observations are normally distributed, that there's this linear structure to them, they're additive, and that the variance is homogeneous across observations. It's kind of hard to show independence graphically, but just know that that's a major assumption. Right, and so the main departures just add non to the assumptions. The prefix non are non-additivity, non-normality, non-independence, and in the old days, non-constant variance or inhomogeneous or heteroscedastic variance. And these are just some of the classical and contemporary ways to deal with departures from the assumptions of the linear model. As a matter of fact, all of the more complex manifestations of the variance components model are made complex by virtue of accounting for the assumptions, departures in the assumptions of the model, following any of these methods. All right, so I want to start with the univariate version and think of a linear regression model. We can model a given phenotype denoted by Y as a multiple regression of Y on however many covariates we want to include in our model. They can be representative of sex, age, however many covariates you want, and then their corresponding beta regression coefficients, right? And here P is our unobserved random variable designated as a model of the error term. We can model this error term as the sum of unobserved additive, genetic, and environmental effects, right? If we assume that the genetic and environmental effects are completely uncorrelated, we can write the covariance decomposition between any two observations or the phenotypes between any two individuals as this function involving twice the kinship coefficient. I'll get a little into this later, times the additive genetic variance plus this Kronecker delta times the residual environmental variance. Kronecker delta is just an indicator variable. It's 1 if individuals I and J are the same, 0 otherwise. And contingent on these side conditions here, that covariance decomposition gives either In the case of individuals, self comparisons, individuals I and J are the same. It gives the standard variance decomposition equation. The phenotypic variance is equal to the sum of the additive genetic and residual environmental variance. In the case of non-self comparisons, the covariance degenerates to this the additive genetic variance weighted by the extent to which the two individuals are related. All right, and so that's the univariate version. Here's the multivariate version, and it's just writing it in terms of matrix algebra. And here's the instead of a single scalar variable, we have a vector of phenotypes. It's equal to this. This is the multivariate linear model. It's a sum. We modeled the trait vector as a sum of a fixed effects component and a random effects component. This fixed effects component, this is just a matrix generalization of the regression part of the model, the fixed effects part. All of your covariates multiplied by your regression coefficients. All right. If you were to carry out the actual multiplications, it would just be a vector of individual level regression equations. Okay. And these vectors of random vectors of genetic and environmental effects represent the random effects, okay? All right, so there's two main parts to the overall linear model. There's a model for the mean, and we modeled the mean of the phenotype vector as this matrix generalization of the regression model. X is the matrix of the mean and the covariate effects, and beta is the vector of the mean and regression coefficients. Okay. All right. And then here's the namesake for the variance components model. If we assume that the genetic and environmental vectors are uncorrelated, we can decompose the variance covariance matrix into this sum of 2 times the kinship matrix times the additive genetic variance plus the identity matrix times the residual environmental variance. And this is simply the matrix formulation for the standard variance decomposition. All right. We assume that the trait is multivariate normal in distribution, and the strict definition for a likelihood is that it's equal to, in this case, the multivariate normal distribution up to an arbitrary multiplicative constant. But downstream when we perform our inferences, we're going to take a likelihood ratio, a ratio of 2 likelihoods. That constant under a natural logarithm becomes additive, and they cancel out, right, when you take the ratios, right? So essentially, we're just concerned with what's called the kernel of the log likelihood, and this is just the natural logarithm of the multivariate normal distribution. And this is an overview of what I just said. This box term, the mapping didn't come out. That should mean is distributed as. So here's the multivariate linear model. We modeled the trait vector as using a fixed effects model and a random effects model. And the trait is assumed to be distributed according to this multivariate normal distribution. Delta here is just the residuals vector, the observed vector minus the mean. And then here's the likelihood. The kernel of the likelihood is just equal to the natural logarithm of the multivariate normal. Right. Now, earlier I said one of the main assumptions for the linear model is the independence of observations. However, if we're doing statistical genetic analysis on families, the data are inherently non-independent, right? And so we have to come up with a way to account for the departure from that assumption of independence, right? And we use it by, or we can address the departure by using this concept of identity by descent. I'll just say IBD from now on. The term IBD refers to the fact that alleles segregating through a population can be identical by descent if they are derived from the same common ancestor. Right? If they're not, and they're identical by state. Okay, And from this concept of identity by descent, we get the concept of the kinship coefficient and relatedness. Relatedness is just twice the kinship, and then the kinship matrix for a given family. Right. The equations have been known for a long time for how to compute your kinship coefficient based on the probabilities of allele sharing for 0, 1, and 2 alleles shared. And I'm just giving a table. I'm not going to go over those equations, but I'm just giving a table of some of the more important relationship types for MZ twins, parent-offspring, different types of sibs, grandparent-grandchild, all the way to unrelated. And based on these relationships and their expected IBD distributions, we can compute the IBD or the kinship coefficients. Okay. And I just want to show you what twice the kinship matrix might look like. And this is just a simple nuclear family, mom and dad and mom and 3 kids. And of course, everyone, along the diagonal that expresses the self-self comparisons, and everyone's fully related to himself or herself, whatever the case is. And dad and mom are, related, have a relatedness of 1/2 with each of their kids. And the kids, for a different reason, have a relatedness of 1/2 with each other. And that's just a simple, for five individuals in that pedigree, or that nuclear family, you have a 5x5 matrix. But for larger families, this is where you really need programming. And this is one of the things that SOLAR does automatically. When you load your pedigree, it automatically computes the kinship matrix for your family. And this one's a family of 171 individuals, so the kinship matrix would be 171 by 171. All right, so SOLAR is really more than just a stats package. In particular, it's a maximum likelihood based statistical package. And it really does just 3 things. Okay, need this. The first thing is it computes the likelihood, for our model, the maximum likelihood for our model. It computes the parameter estimates that make the likelihood function a maximum, the parameter estimates under your model, and it computes the standard errors of the maximum likelihood estimates. So these are the 3 main things that the SOLAR package computes. By the way, from the likelihood, we can compute the likelihood ratio test statistic, and in that way, make our statistical inference. The way you compute that is the likelihood ratio test statistic is minus twice the difference of the log likelihood under the null hypothesis and the log likelihood under the maximized version of the model. All right, this is just a bivariate likelihood surface. All right, the maximum likelihood estimates will be found on of course, obviously on the maximum of this surface. And SOLAR is just like a mountain climber who finds the peak. We get happy. All right, so now I want to talk about some extensions, basic extensions from this basic polygenic model, right? I want to talk about, the first one I want to talk about is pleiotropy, the extent to which a gene might, or a small number of gene types might influence more than one traits. Extension to account for linkage, genetic association, and then this novel extension to be able to efficiently do a sequence analysis for a large data set. Okay. So I want to talk about pleiotropy first. And to introduce that term, I need to make a distinction between the 2 ways in which the term multivariate is used in statistical genetics. And the first way is the most common way in which multivariate is used. And we say that a trait is multivariate normal within families, right? Now, I asked this question, what would the trait distribution be in a sample of unrelateds? Usually, if it's continuously distributed, it'll be just a univariate normal. But the reason why we posit a multivariate normal distribution in pedigrees is to allow us to be able to account for the non-independence in that family, right? And we can account for the non-independence by way of the kinship matrix, because that will give us a measure of the extent to which individuals are related, i.e. non-independent. All right, the other way in which we use multivariate, and that's the one relevant for this topic, pleiotropy, is with respect to multiple traits belonging to the same physiological or anatomical system, say like traits in a brain structure study, right? So obviously if they belong to the same physiological or anatomical system, they're very likely going to be correlated. Right? We kind of want to develop a model to be able to make an inference on whether or not they're correlated, and if they are, the extent to which they are correlated. All right, and this is just an equation from Falconer's standard Introduction to Quantitative Genetics textbook. And it's the decomposition of the phenotypic correlation. Here, rho P, rho G, and rho E are just the phenotypic, additive, genetic, and environmental correlations. And H squared sub X and Y are the heritabilities for traits X and Y. And that's just how the equation shakes out. Right? We can use that equation is embedded in the what's called a bivariate model, where we can use that model to estimate the genetic correlation coefficient. And then on estimating the genetic correlation coefficient, we can then test if there's pleiotropy, and if there is pleiotropy, if it's complete or partial. All right. So we can model the non-independence of two traits in terms of their covariances, and under this model, we can estimate key parameters that say a lot about the multivariate structure of traits. In particular, the cross-genetic correlation can be used to evaluate potential pleiotropy. And maybe I should have put this definition earlier. And pleiotropy at its simplest, to say the most basic, is when a single gene accounts for more than one trait. Or you can think of it as a small set of genotypes accounting for more than one trait. All right, and oops, this one I didn't catch. So there's this kind of linear relationship between the increasing pleiotropy and increasing sharing of additive genetic variants. All right, I'm going to give an example later of pleiotropy, so just hold on to those ideas. Right now I want to show how the basic polygenic model can be extended to the Q-tail level. And we just posit now a novel random vector for the Q-tail effects, right? The quantitative trait locus effects, okay? Denoted by this Q vector here. And we assume that these are uncorrelated. We can decompose the variance covariance matrix as this sum. Here's the original polygenic model, but now we just add this this pi matrix of multi-point IBDs estimated from marker data, and this multiplied by this the variance, the Q-tail variance. Right. So I want you to think of this twice the kinship as the expected genome-wide relatedness. Right. So that's like the theoretical relatedness for a given relationship pair, for a given relationship type. This pi matrix is the empirical relatedness estimated from marker data. Right. So you have it's empirical and the local about a certain point. So this model is for a single locus, somewhere along the genome. All right. And this pi matrix gives the local pattern of relatedness estimated from marker data about that locus. Okay. All right, and in the traditional matrix metric to assess the significance of a linkage result is the LOD score, and it's just a function of the likelihood ratio test statistic. Setting the Q-tail variance to 0 and then maximizing it and estimating its likelihood and forming the LRT that way, divided by two times natural logarithm of 10. Generally, a LOD score greater than 3 is deemed significant. right? And this is an example. I decided to use this to kill two birds with one stone. It's an example of pleiotropy and linkage. And here, I'll take the linkage part of the figure first. Here we see that there's a QTL somewhere around 150 centimorgans that's linked with potentially causal variant that influences variation in FSI, stands for fasting serum insulin, leptin, FSI, and sum of skin fold. It's an anthropometric measure of adiposity, FSI and body mass index, FSI and natural logarithm of serum triglyceride. And so these peaks are right on top of one another. And so there's a QTL that's influencing their variation. Now, you can also test formally whether or not the QTL correlation is different than zero for this trait. And Ravi Dugarala, John Blangeros in this paper, and they formally tested if the genetic correlation is different from zero, and they were able to reject it. So they found that the QTL influencing fasting serum insulin is highly correlated with the QTLs influencing leptin, sum of skin fold, body mass index, and triglyceride. So this is a nice example of how a single QTL can influence, by way of pleiotropy, here in this case, 5 traits. All right, and so for my example for GWAS, I want to give an example from our work on GWAS of substance P. And substance P is a member of the tachykinin or neurokinin family. It's mapped to the CNS and PNS, and its distribution coincides with sites of the brain associated with anxiety, stress, and depression. It's implicated in brain disease, in Alzheimer's, alcoholism, stress response, depression, anxiety, and brain-related inflammation. So this is the model we use. You might recognize this. This is the linkage model, right? So we use a joint linkage association GWAS, right? And so the linkage component is estimated using this model that I talked about earlier. This is the QTL variance. And you don't see the association part of the model because it's embedded in the fixed effects part. We modeled the SNP as the causal SNP or potentially causal SNP as a covariate effect in this matrix of covariates. And we make our inferences based on the corresponding regression coefficient for the SNP in that beta vector. And the likelihood vector has the same form. I mean, the likelihood has the same form as given earlier. Okay. So using that model, we were able to detect from this joint linkage and association, GWAS, 2 variants that were important in substance P variation located on chromosome 2 and chromosome 9. And I have enough time to go over the result on chromosome 9. So we found a variant, this RS657152, and about 500 kilobases from that is this DBH gene for dopamine beta hydroxylase, and it's involved in the stress response, as is substance P. So this is we expect this to be a candidate gene worthy of further pursuit. All right. So that was an example of how we can extend the basic polygenetic model to joint linkage and association to do a GWAS. Now I want to show how we can use these ideas and extend it a little to analyze next-gen sequencing data. And one of the greatest computational impediments for using the traditional approach is the necessity of computing the inverse covariance matrix and U for each and every SNP, right? And the problem is with this guy right here. The likelihood requires the inversion of the covariance matrix, so this matrix inverse, right? And not only does it have to be computed for every SNP, recall that this is a maximum likelihood algorithm, and it's not like the algorithm starts and the first iterator it finds the maximum. All such algorithms have to go through a number of iterations, and each iterate requires a brand new inversion of the covariance matrix. So it's some variable number of iterations times however number of SNPs you have. It becomes an extremely computationally prohibitive task to have to do all of these inversions again and again and again, right? So this eigentransformation transformation approach completely bypasses the need for a matrix inversion and consequently makes genetic analysis much easier and faster. Right? And so we can just write the eigenvector decomposition, the EVD of the kinship matrix, using this the orthogonal matrix of eigenvectors and this diagonal matrix of the eigenvalues of the kinship matrix. And the eigenvalues of the phenotypic covariance and kinship matrices are related by this simple linear function of the heritability and the eigenvalues of the kinship matrix. And we can re-express the EVD for the covariance matrix using this linear relationship between the eigenvalues of the phenotypic covariance matrix and the eigenvalues of the covariance matrix. Under the EVD for the kinship and the covariance matrix, the phenotypic covariance matrix, the orthogonal matrix of eigenvectors S are identical, so we can use the same, those same matrices. And so we do the EVD of the kinship matrix. We use that S matrix to perform this transformation. This is a linear mapping. Takes this vector of residuals of non-independent data and makes it essentially independent. If you were to write out figure out the likelihood, you get this essentially it's a sum of univariate likelihoods. But the important thing I want to draw your attention to is that there is no need for matrix inversion here. The need for the matrix inverse completely drops out, and it's essentially the same thing as a likelihood computation for the same number of unrelated individuals. So it makes it really, really fast, or as fast as analysis of on the same number of unrelated individuals. And that's what I see here. But more than that, this eigensimplification approach leads to simple formulae for power analysis of models under a variety of study designs. And a lot of this work was reported in Blangiero et al. Advances in Genetics last year. And it's my talk. Oh, you have yours?
Now that we know the basic genetic model, we shall go and see what SOLAR actually is and how SOLAR actually works, especially when it comes to genetic imaging phenotypes. So I'll give a little bit of the historical perspective, then I'll talk very shortly about downloading and installing SOLAR-Eclipse because it's such a simple and easy matter. Then I'll be spending some time on discussing on how to create SOLAR analysis directory, specifically how to make pedigree files, how to make marker files, and how to make phenotype files. Then I'll be talking about common analysis types. As Dr. Diego pointed out, we have a variety of genetic analysis that we can perform, so trying to match the type of the analysis to the type of the contrast will take a little bit of time to discuss. And then I'll be talking about how we can use SOLAR-Eclipse for specific analysis that somewhat novel and emerged as the result of consortia-type projects, and more importantly, our ability to increase power of genetic discovery by using data that's collected locally as well as data that's available publicly, such as ADNI, for example. So SOLAR-Eclipse is an extension of SOLAR package for imaging genetic research. It's developed for multi-platform perusal, so we support PC, Mac, and Linux, and we can analyze both discrete and continuous traits, and there is a wealth of genetic methodology that's incorporated into the package already. So we have polygenic, quantitative trait, and GWAS analysis. And more importantly, this can be done in both related and unrelated individuals. And as we'll show you later on, you can actually combine related and unrelated individuals to boost the power. And it implements functionality of three sort of standard genetic tools, including MENDEL, FISHER, and SEARCH. So SOLAR was built somewhat as a replacement for MENDEL, and it was specifically intended for gene mapping calculation, quantitative trait linkage analysis, pedigree separation, multi-point linkage and quantitative trait mapping, allele frequency estimation, paternity testing, and sort of the standard genetic counseling work that's performed in disorders such as cystic fibrosis, various dystrophies and myopathies, and many others. FISHER is a genetic analysis of quantitative trait whose variability is explained by polygenic inheritance and environmental forces. So here we are talking about sort of standard inheritance model, standard twin type modeling. And it provided function for additive genetic analysis of continuous polygenic traits, primarily heritability and pleiotropy, or otherwise known as genetic correlation. So both MENDEL and FISHER rely on maximum likelihood estimator. And as Dr. Diego pointed out, we use genetic likelihood calculation to basically where we consider the variability in the trait to be multivariate normal, and multivariate and univariate analysis are supported, and proband correction and robust outlier detection is implemented. And so this kind of calculation is done using the maximum likelihood estimation engine called SEARCH. SEARCH is really a name that comes to us from 1960s. I believe the first implementation of this algorithm was done in a scientific language that preceded Fortran, and the follow-up implementation was done in Fortran, and since then it was still used in Fortran. And in fact, the part of the SOLAR that does this search analysis is still built as a Fortran library. So talking about legacy code. So search algorithm is the maximum likelihood estimator engine for both MENDEL, FISHER, and essentially SOLAR. And it's an optimization routine, and it works within user set bounds and limits. It maximizes a cost function by sampling a function over the grid and implements the least square and user-defined estimators. And John has optimized the version of search for discrete trait analysis, and it's called Optima, but either one is fairly obscure, and you won't have to interact with them when you use SOLAR. So what is SOLAR-Eclipse? This is sort of the block diagram and the way you're going to interact it. It takes both Nifty and text format input, and you primarily interact with a TCL interpreter. It's very much like our interface. If you know how to use R, if you used R before, likely you have played with very similar interface already. So the TCL interpreter is the part of the program that we'll call the C++ code that's integrated with TCL, and the output is either going to be presented in text or binary nifty output. And then, of course, you have C and C++ coded parts of the Search Optima and Fisher and MENDEL. What have we done since last year? So the last year we primarily spent on improving the polyclass functionality. And now the polyclass functionality became standard in Solar. Basically, polyclass functionality provides for combined analysis of multiple pedigrees of both related and unrelated individuals. And it provides with both mega and meta analytical matrix. It also provides for additive genetic effect modeling that can be performed either per class in a combined pedigree, as well as for the fixed genetic effect modelings that can be performed per class or in a combined pedigree. And we have done some improvements in file handling, thanks primarily to the Dr. Bennett Lundman, who identified some error in the file handling. So SOLAR-Eclipse is available for download and installation freely at our Nitric web page. Installation is relatively simple. You just untar the file, and the first time you execute it, it will ask you for the software key license, which is again free and typically available, and you only have to do it once per user. So just send an email with a code to the email address, and you'll get it. So we are just commissioning our new website, which should have instruction videos, how-tos, and example files. And there is a main solar manuals that are available at the Texas Biomedical Institute website, but they're mainly directed to geneticists. So we are trying to sort of rewrite them for the sake of imaging genetics people who know imaging but might not know a lot of genetics. So once you have installed the package and once you have the software key, you simply type Solar and the TCL interpreter starts, and then you can type any command among, I think there are about 200 commands in the most current distribution of Solar. And so like command like polygenic, you type it into the command prompt, and TCL interpreter reads the Solar TCL file, which codes for all popular function, including polygenic, and it executes that polygenic function, which goes into the argument list and starts going through the existing global variables. It chooses among several analyses and calls upon compiled functionality for computationally intensive steps. So, sorry, I'm a bit technical in my description, but some people like it. So, so TCL is a tool command language. It's very similar to shell script such as bash and sh, and all Solar commands are TCL function. So you can examine, modify any command in Solar by simple show proc command. And in fact, if you say show proc command and then type new command.tcl, it will create a copy of the original TCL script in your directory. Moreover, you can open that copy with your text editor, add or subtract some functionality, and the next time you start Solar, this new command.tcl will actually appear in your command list. So Solar is easily modifiable. So any user can get under the hood and change functionality. all projects in Solar are organized by directory, by default. You can change that. As I said, you can go onto the hood of the Solar and change it. Whether you want to do it or not depends on your particular situation, but I prefer to use the standard distribution where all projects are organized by directory. When you start Solar in that directory, Solar will read all the default files from the directory it is started from, and that includes pedigree and default phenotype files. Typically, we expect the directory to contain the pedigree file, which includes the kinship matrix, which in turn defines all the familial ties among the subjects. Whether the subjects are related or unrelated, you still have to have the kinship file, therefore you have to have the pedigree. So the first step that you do when you start your genetic project is you have to code the pedigree. I know that sounds very intimidating, but in actuality, it's a very simple process. You can do it in Excel and then just save it in the CSV file. There is one caveat, a little mistake that commonly gets people who use Mac. Macintosh users should save it in the Windows CSV format or comma-separated value format, because the way Linux systems or other systems work is they interpret the carriage return or a new line or a symbol that denotes new line as in the Windows format rather than in the Mac format. So pedigree file should define subject ID. This is the field that is completely going to be up to you. So for example, if you get your genetic data out of Illumina chip, then typically you're going to have subject ID there already. So might as well use that rather than go into trouble of recording all your subject IDs. You have to provide ID for both parents. So every subject that you use in active analysis has to have father and mother, and they have to have IDs. So the only subjects who do not have to have familial IDs are the founders. And Solar expects never to run any genetic analysis on the founders. So you have to, even for the twin studies, because I know for like OpenMX, you don't have to provide familial IDs, but with Solar, that's requirement that has to be there. So you have to provide, basically generate familial IDs for your active subjects. Obviously, you have to provide gender or sex, and that can be coded either numerically as 2 or 1, or as M or F, male and female. Then you need to provide family ID, albeit that's an optional point. Then you can also provide monozygotic twin label, which is important for twin studies, but again, it's an optional point. And another optional point is class, and that's used for defining super pedigree from several independent pedigrees. So defining pedigree. So as I said, each active subject has to have ID, family ID, gender, parent ID, even if you don't use parents for the analysis, and a label for being a twin, monozygotic or otherwise. Additional variables, class and house, they're optional. One of them specifies subjects belonging to a different pedigree. The other one specifies household to study environmental effects, something that twin analysis studies commonly do. So here's an example of pedigree for a Q-team twin study. And that study is a collaborative research between UCLA and University of Auckland, right? NEDA. Queensland, University of Queensland. And I'm proud that I have made that file, so I can tell you all about it. So because I mostly work with NEDA, I gave the subject numbers UCLA prefix, and so you have ID of the subject, such as UCLA 8000321. Then you have FA, which stands for ID of the father. Then you have MO, which stands for the ID of the mother. Then you have gender. Then you have family ID. And this is a twin study, so we have monozygotic twin label. And that monozygotic twin label, in this particular file, I just assign it the family ID. So family ID and monozygotic twin label ID are the same. So after I defined the twins, I basically had to invent parents. This is a twin study, so they did not image or ascertain parents in any way, shape, or form. So I simply created IDs for the parents, and obviously I assigned them the right gender. So, father is 1 and mother is 2, or vice versa. And this is an example of interacting with Solar. You type Solar, and you are given sort of this, screen, and then it goes into this R-like interface where you have a command prompt, and you can type any command. You can use bash commands because it will actually interpret those bash commands for you. So, for example, when you type ls in the Solar prompt, you're actually going to be given the content of the current directory. And it just so happened that you have the file called gobs_UCLA_pedigree.csv. Again, it's a simple text file where commas are used to separate values. And I give a command called load pedi, which stands for load pedigree, and then I give the file name. And Solar reads that file, it analyzes its content, and then if I type ls, I can actually see that in addition to the original file, several more files appeared in the directory, including household matrix, pedigree info file, pedigree index, pedigree index.out, and phi2, which is the kinship matrix. As simple as that. All of those files are simple text files. You can unzip them, and you can read them out in Excel or any other package of your choice. So, for example, if you'd like to calculate a kinship matrix for your family, you can actually code it in Excel, and then you can load it in Solar, and then you get a nice matrix of your kinship coefficients. I mean, you can actually do it then with genealogy plotting programs, and then you create your family tree using a scientifically prescribed software. In addition to coding your pedigrees manually, which I have to do most of the time, you can import them from a variety of packages. So it's very helpful if you collaborate with somebody who already has a statistical geneticist on staff, and they already have that pedigree coded in the multitude of packages, including Search, Sage, Pub, IBM Matrix, and many others. There is actually a chapter devoted to the importation of pedigrees, but this, of course, only matters if you have, projects that involve multi-generational pedigrees like Amish, where you basically have pedigrees that are 10,000 and more subjects, and coding them by hand would be, quite a chore. Next, let's create a genotype file, or otherwise known as SNP file. Solar uses a simple marker format. It's again a CSV file with a header. You either have to have ID or EGO column. and that's used to define subject IDs. So it would look, so ready-made genotype file would look something like that, where you would have ID, you would have the name of the genotypes, and then you would have dosage value for each of the genotypes. You can also read Plink genotype files. Many of the genetic tools use Plink genotype files, and Plink genotype files are very commonly sort of used to transfer or share the genetic data. So Solar is a bit quaint when it comes to the Plink genotype files, mostly because we haven't quite gotten our hands to fixing all the issues. So it's still work in progress. As for now, it will only work with dosage files, where minor alleles are coded as 0. So each subject will have values as 0, 1, or 2, or fractional values, denoting the dosage of minor alleles. We have several converters, so contact me if you need to do it. Also, Enigma offers an SNP extractor script that will create genotype files from either Plink or imputed versions of genomic files and form them into a readable, Solar readable list of genotypes. It's relatively simple. Now, so we have covered creation of the pedigree. We have covered creation of the genotypes. So now it's time to talk about phenotype files. So pedigree and genotypes are probably going to be stable for the life of the project. You only have to do them once. With phenotypes, you can have a multitude of phenotypes. So you'll be creating a lot of phenotype files as you progress with your research. So Solar phenotype files are also in a simple CSV or comma-separated value format. Again, the only requirement is that header must include either ID or EGO column. If you attempt to read a phenotype file that has neither, the Solar will complain and refuse to do anything with the phenotypes in that file. So identifiers are used for the ID field. And typical file for a continuous trait would have, for example, ID of the subject, age of the subject, sex of the subject, gray matter thickness, and then you basically can arbitrarily name the phenotypes you want to analyze in terms of the genetic processing. There is an extension of the phenotype file to incorporate binary imaging data. And in this case, the CSV header should identify the format of the trait using a semicolon notation. Specifically, you would say something like gray matter density, semicolon, nifty, or gray matter thickness, semicolon, gifty. And file name is provided for each subject instead of a continuous variable. And semicolons can also be used for volume identification in a 4-dimensional nifty file. So here's an example of a phenotype file that identifies binary traits. And again, for a phenotype file, you feel free to mix continuous and binary traits. So here, for example, you have an ID. ID is compulsory field. It has to be always there. You have age, sex, for example, average FA values that are now just continuous trait. And then you have FA values that the individual FA maps per subject. And you see the FA values are stored in a single 4-dimensional nifty file called gops_fa.nii.gz, And semicolon is used to identify which volume in that four-dimensional file belongs to which subject. Relatively straightforward. Using this binary phenotype, you can now perform genetic processing on individual voxels. So specific voxels need to be defined before the processing, and individual voxels can be identified as voxel X, Y, Z. And there is a command in Solar. Solar has extensive help built into it. So if you just type help and command name, you should get a helpful message explaining what this command do and how to use it. So for example, if you type help voxel, it will tell you how to set and save current voxel position. Now, performing genetic calculations on individual voxels can be a very cumbersome and tedious processing. So instead, you might want to define a mask. Mask command defines a set of voxels by basically defining a volume of the same intensity. So if you type help mask, it will read image mask file, which is supposed to be in the same coordinate system as your phenotype file. And then you basically set the current voxel intensity for the mask, and then Solar will go around and analyze all the voxels that fall under the voxels of this intensity in the mask. If you ever used FSL, I'm sure this type of processing is going to be very familiar to you because we basically stole it from the FSL package. And for binary traits, you can define output to be a binary file. So imaging trait analysis can be saved into nifty multi-volume file. And you simply specify it by giving a command output volume and a file name. It will copy the header information from the current trait file, and then it will save several measurements. I think this information is slightly out of date. I think right now we are saving up to 10 variables. So it's going to be a nifty volume. It's going to be a 4D nifty volume of 10 traits. And the first one is going to be heritability or the primary measurement that you are trying to access. Could be a genetic correlation, could be something else. Then you have standard error for the primary measurement that you're trying to assess. Then you have a p-value, and then you have percent variance explained by covariates. And there's going to be several more volumes that were requested by people doing those analyses. Genetic analysis, especially genetic imaging analysis, can be very computationally demanding. Therefore, it's practical to use parallel computational clusters for analysis of, large number of traits. And masking command is basically built in to simplify the execution in the SGE type environment, and SGE is a Sun grid engine environment. So you can use mask to parcellate space with respect to your cluster topology, and then it will save output in different files. And then you submit them all as separate jobs, and then you add those files using FSL math command together, and you get your final result. Now, all that I have mentioned so far, it's a relatively old development. So what we spent the last year on developing are the mega and metagenetic analysis. Mostly we have done it because of the need of analysis for large consortiums that have collected imaging and genetic data, specifically the Enigma consortium. So Solar Engine is very flexible and very powerful. So it works with pedigrees of random length and random complexities. So Solar can work with families, it can work with twins, it can work with completely unrelated individuals. And this can be used to a great advantage because we can combine separate pedigrees at the raw data stage. So instead of using meta-analysis, which is typically going to be underpowered, or you're going to lose a lot of power by using meta-analytical analysis, you can actually combine your data at the raw data state. And in this case, you're only losing maybe 2 degrees of freedom by including a pedigree of, for example, 500 people. So your total gain in power is going to be 498. So this is sort of our dream of boosting the N, or dream of boosting the power of genetic discovery. I mean, it's a very simple concept. I mean, we are basically trying to merge small population into a synthetic pedigree, not unlike a pedigree that merges multiple families into, a pedigree. And then we can perform genetic analysis as if we are working in one large extended family that can have both related and unrelated individuals, which is not at all uncommon. So the advantages of the mega-analysis is that it makes it more powerful in terms of the number of preserved degrees of freedom than meta-analysis. And that means that the test of significance is performed on much higher number of degrees of freedom. And that's, of course, done by combining samples, smaller samples, into a single superset or super pedigree. Another fundamental advantage may be that by analyzing or combining data at the raw stage, you have less weighting by discrepancies and subject numbers, and therefore you are less affected by variance in standard deviation among cohorts, as well as by the variance in the number of subjects in your cohorts, because for meta-analysis, you have to weight your data by either standard deviation or by the number of subjects. And both of those approaches come with certain caveats, and Neda will go into the details. And more importantly, by having them in a single pedigree, this provides us with the opportunity for testing heterogeneity of genetic effects. I mean, this is the field that we have not quite scratched even the surface. So we all sort of assume that the genetic effects are going to be similar between different ethnicities, between different pedigrees. But what if we actually have to test it formally? There is relatively little methodology to do this type of processing, especially on the imaging data. But then, of course, you have certain advantages of the metagenetic analysis. One of them, it's a lot easier to perform, and it's a lot more acceptable because it's a commonly used scientific technique. It also can be said that this synthetic heritability or any other genetic measurements that are extracted from synthetic pedigrees, and by the same token, genetic measurements extracted from fixed effects, may not be well defined due to population differences. This is, again, comes back to the point of heterogeneity of genetic effects based by pedigree, based by geographic location, based by ethnicity. So how does one proceed with performing this mega or meta-genetic analysis? Well, it's actually very simple. You make a pedigree for each of your smaller pedigrees, right? So, or hopefully somebody has made them for you. All you have to do now is basically assemble them all by copying them into a single Excel spreadsheet. And you add that class field. That class field defines all subjects belonging to the same group in very much the same way household or house is defined all the members of the family who live under the same roof. Now, to make this more scientifically valid, all the sporadic model analysis or the sporadic model is fed separately for each class. So what is sporadic model? Well, sporadic model is the model where we account for covariates. And because those covariates can be different from one sort of population to another, this is done separately. And Neda will show it on her example, where she, for example, combines data from twin studies, where the age range between subjects can be very small, to family studies, where the age range per family is typically very large, because you have to have multiple generations. And individual data sets are normalized by inverse Gaussian normalization. And this ensures the equality of the distribution and variance of each trait. And then several polygenic tests are performed, specifically test of significance for each of the pedigrees separately, then crosswise test of difference of genetic effects for each pedigree, and then test of significance for a combined pedigree. All of this is performed using a polyclass modeling function. Polyclass function will model additive and fixed genetic effects across pedigree. It is performed per pedigree modeling of genetic effects, and this is useful for meta-analysis or analysis of site-specific effects. And then it performs combined modeling of genetic effects, and that's how you hope to improve the power of genetic discovery, as well as you sort of study the genetic effects that are generalized additively across the cohorts. So here's an example of megagenetic association analysis. The idea was to perform association analysis across more than one cohort or across more than one pedigree. In our example, we used 4 cohorts. GOBS contributed 800 subjects that belong to large families. Q-Team UCLA study has contributed 600 subjects, mainly monozygotic and dizygotic twins. NIDA IRP has contributed 400 completely unrelated subjects, and Tao's cohort contributed 300 twin and sibling studies. So you can see 4 cohorts, each of them basically being very much different type of genetic study from the others. So we have standard family study, we have a twin study, we have a study of unrelated individuals, and we have a sample that combines twins, siblings, and cousins. So megagenetic analysis makes this processing very, very simple. You basically type polyclass 0-3, which indicates that you would like to include in this analysis all 4 classes. Or you can say 0, 1, 3. And this way you perform this modeling on just 3 out of 4 classes. And this is, of course, is done for sort of permutation type analysis of genetic effects. Then you provide the max SNP option, which tells the Solar that this is going to be the SNP for which you would like to maximize it. And then you provide in-trait option. And this model of association, and this will model the association between the trait and the SNP, and it will do it separately in each of the classes. And in-trait option tells that you would like to perform inverse Gaussian for each of the pedigrees separately, and this amounts to performing standard metagenetic analysis you model genetic effects separately per cohort, and you combine them at the level of results. So what is actually going on under the hood once you hit the return button and the processing started? Well, those are your original phenotypes. And as you can see, because the data was collected at different scanners, there is quite a bit of difference in the distribution of the traits. Tao's cohort and GOB's cohort and NIDA cohort and Q-team cohort all have very different average values, but the individual samples are more or less normally distributed as we would expect. A sporadic model is now fit, and all the covariates are removed from each of the pedigrees separately. So the sporadic model is fit per cohort. In other words, we perform the regression of age, gender, and ethnicity effects separately because we do expect them to act separately in separate cohorts. After this, our samples are still more or less normally distributed, and now there's zero mean. But again, there is quite a bit of kurtosis and quite a bit of heterogeneity, or at least apparent heterogeneity, in the distribution per sample. So we fit inverse Gaussian normalization, and lo and behold, all our data looks more or less uniform and more or less homogeneous. So we can actually now perform the test of the association per sample individually. And it actually looks pretty promising, except the particular SNP has relatively low prevalence in both GOB's and Tao's cohorts. So we only have one subject with this with homozygous minor allele, and only two subjects with homozygous minor allele in GOB's and Tao's cohorts. But then we have this trend, the additive genetic trend between heterozygotes and homozygotes for the major allele. So there is this trend towards higher FA values in both cohorts. In Q-team, we happen to have 13 homozygotes for minor allele, and we have a fairly good number for the heterozygotes, and we have a fairly good number for the homozygotes for the major allele. So here the additive genetic model looks very, very nice. So we have this standard, very pretty distribution. In NIDA, we actually have about the same number of subjects, but again, the linear model looks still acceptably well. So we can see that in all four cohorts, we actually have a trend towards significance of the association. And in fact, it is significantly associated in Q-team, but the variance explained by the genetic variance is rather small, so the association is only reaching suggestive significance in both GOB's and Tao's cohorts. And I think it is significantly associated in the NIDA cohort, so we can still fit the linear model rather nicely. So by looking on it at the metagenetic level, we actually see that we don't have complete concordance between all four cohorts, but at least the direction of the effect is very similar for each of the cohorts. And the reason why we don't have association in the two cohorts on the left is because we simply don't have any homozygotes for the risk allele. It's a relatively low minor allele frequency gene. Now, can we model this in the entire super pedigree? Well, we can, and we basically just type the same polyclass command, except now we add the comb option. And this combine option will actually model the association between the trait and the SNP in the megagenetic analysis, where the classes 0, 1, 2, and 3 are added into one superfamily or super pedigree, and where we're actually going to boost the number of homozygotes for the minor allele to a quite substantial number. So once you combine all the subjects into a super pedigree, you actually see this very beautiful Gaussian distribution, suggesting that you have a nearly ideal field to plant your seed, so to speak. And once you analyze this in every single subject, and this is 285, you actually have a sufficient enough number of homozygotes for the minor allele where the trend is fitting very, very nicely, and you achieve a significant association, or in this case, it's replication, and it's for the disk 1 polymorphism. Again, this is still very much work in progress, and so we are very much looking for some brave souls who will download and break this package. We are looking for people who will sort of put it to use and break it. And this is our way to improve stability by offering it to everyone and then sort of soliciting the feedback on what they like and what they don't like. So it's best to contact me to discuss your project, and then we'll attempt to see how we can work with you to get the solar eclipse sort of fit and stable for your particular application. And in next year's workshop, we'll continue this discussion of new solar eclipse features, and specifically in terms of performance and memory optimization strategies. And by this time, I hope we'll be able to perform voxel-wise megagenetic association or analysis of fixed effects in the entire Enigma DTI sample of presumably over 5,000 subjects. And hopefully next year, Tom Nichols will inform us on a better multiple comparison correction, and we'll talk about more integration of solar eclipse with image analysis and pipelines, and that's our collaborative work with Dr. Landman. And I'd like to acknowledge my collaborators, John Blangero, Charles Peters, David Glant, Tom Nichols, Bennett Landman, Neda Jahanshad, and of course, Paul Thompson, and of course, NIH for generously funding our research. Shall we have 10-minute? Yes, I think that's a good idea.
They're running the next two back to back, right? There's no break between the next two? I don't think so. Well, anyway, I'll just set this to the guy. 'Cause I'm not the next, I'm the double next.
I think the other one's getting...
Right, the other one's up there. No one else is stupid enough to do a live demo.